And maybe as a computer scientist, you could do some kind of infection on one, some pattern on one. Okay, so here I'm trying to be a little bit precise without invoking like any inductive principles. Yes.
So there's a single object like one, but there are a lot of these multiple like maps in the A.
No, I'm saying one is just like it's a unit category, so it's got nothing else except for one object.
Okay,
And
but
of course that's not one identity more than one object.
oh, I was asking, can there be more than one? For example, could one contain like a single object A, but several different arrows in A?
No, because I want one to be the category of just one object.
So by definition.
Yeah, and like nothing else. Okay, so we have this example, a nice, nice concrete example. And maybe I won't give more examples explicitly on the board, but this is like the most basic example of mapping a tiny little category into an arbitrary one. By which I mean, like you could have other categories, like you could have a tiny little category like this. And what I mean by a tiny little one is just kind of a finite one. And then functors from this into a category C correspond just to morphisms. This is kind of a free morphism in some sense. And if we have a category, let's say a triangle in some sense, like this, then functors from this into C, just you have to map the triangle into a triangle in C. So it's just the collection of functors like that is a collection of triangle, of diagrams, you can make it a little triangle in C. Okay.
So just to double check, the functor, like for each object in C, there will be a functor that takes things to C. But there's no like one functor that like you give a parameter that's enough. Like there's one object for each object in C, one functor for each object in C, and that's all they say.
Yeah. Yeah, you can think about it as being parameterized as well. But that's more common. Okay. Right, so I want to continue with examples about this guy one. So, given, again, an arbitrary category C, there is a functor from C to 1. And who can tell me what this does? This has to go from top C to 1. Yes.
Just lambda x1 or
Yeah.
a or whatever.
Exactly. Okay, and if I have, if I have two objects x and y, and I want to have a function from C x y to 1 AA, right? So really write one obtrude x, obtrude y, but obtrude of anything is A. So I write AA here, right? Do a little simplification already. And what should this function be? Yeah, it's the identity, because that's the only thing that we can do. So lambda f identity I. Okay. So I gave this example for a reason. Also, there's some suggested notation here. So what descriptor could you apply to our category 1? It's a terminal object, yes. Because, okay, we just exhibited a morphism in catch from C to our terminal object. And the other thing we need is that this is unique. But it's definitely unique, right? Because there's only one thing in one. There's only one object and one morphism. So all the objects have to be sent to that object, and all the morphisms have to be sent to that morphism. So we've just proven, and again, maybe it can be an exercise to write this down really concisely, especially if you are unclear on some of the details. So we just made the observation that 1 is terminal in the category of categories. Yes.
So the reason this is unique is two functors will be the same as each other if their functions are the same during the sets.
Yeah.
Okay.
Yeah, because, yeah, I didn't say it very explicitly, but two functions are always the same, both in set and in category types, if they do the same thing to the same objects, if they're point-wise equal. All function technology right now. So we have that two functions are the same if they do the same thing given the same argument. And so, yeah, so since a functor is composed of a bunch of functions, then you have two functors that do the same thing to the arguments, then these pieces of data will all be the same, so then they will be the same function. Yeah.
So, for example, in sets, we can have two different morphics. Like, okay, those can be different. But in category, you have one start point and one end point. Are those always going to be the same functor?
Definitely not. So I mentioned there was some questions last time and before that every set is a category. Given a set, you can turn it into a category by just having the category of all the elements in that set and just the identity ones on those elements. So we have what we give as an example. There is a functor from the category of sets into the category of categories that does exactly what I just said. So it makes it discrete. It also maybe stand for discrete. So we have a functor like this. And I'm not going to define this concept in these lectures, even though I realize that's like I define. But just like for functions, you have injections you might know about. This is a sort of injection functor. You might call it an embedding. In the sense that if you have two sets, and you think about them as categories, so you think about the category, whose objects are the elements of the set, and the little identity morphisms everywhere, then two functors between two categories like that are coming from this functor, are exactly the same as the functions between the original sets. So you can write this precisely as in set xy is the same as in cat delta x delta y. So the functions between these two sets x and y are the same as the functors. So that's one example of many functors in categories. Yeah. So in some sense, the categories, they generalize sets. In the sense that we see sets as a fragment of, speaking categorically, we see the category set as a fragment of the category of categories. So all the things that are true about sets are true in a fragment of categories. And then we have extra sets to study as well. Okay. Right. So we have a terminal object in cat. When we ask guys, what do you think is the initial object in cat? Yeah. Yeah, the empty category. And why do you think that?
There's only one functor from the
Yeah, there's only one functor from the empty category because to any other category, because we have to supply this data and these equations. But if we're looking at the empty category, so really the category with no objects, and then of course no morphisms, we have to supply these functions which start at the empty set. I mean, we talked about how the empty set in set is initial, so there's going to be exactly one morphism out of the empty set there. So there's exactly one collection of data that we can provide to this specification functor, and therefore there's exactly one functor. The functor that just does that. Okay. So let's see. we continue on with more examples of functors, since we're talking about initial and terminal objects, I'll also ask you guys, what do you think is the product in the category of categories? Yeah.
Component-wise product.
Yeah, it's component-wise product. Exactly. So maybe I'll make that an exercise. But just like how for terminal and initial objects, we kind of lifted the fact about those guys in sets to the fact that it's basically the same categories. So it's the same here. So C times B has objects, so it's component-wise, so it has objects, C times B, so we just take the product of all objects. And for the morphisms, then we need to ask what is comm in C times D between two objects of C times D, and those two objects are going to be pairs, right? So we're going to have, now I'm going to, instead of using variables like x and y, I'm going to use non-curly C and non-curly D to do my variables in curly C and curly D. So here I will write C prime and D prime. Okay? So we have two arbitrary objects in our category C times D, meaning two pairs where the first component is coming from curly C and the second component is coming from curly C. Okay? And as I said, this is going to be the product everywhere. So we're going to have space for this. We're going to look at the HOMs in C from C to C prime. And we're going to multiply that with the HOMs in D from D to D. So we kind of think like the objects are pairs of a C and a D, and the morphisms are pairs, one that goes from C to C prime and one that goes from D to C prime. So it's kind of like the morphisms are just pairs and morphisms kind of next to each other. You can like diagram it out if you want to draw a little picture to do this yourself. So first then you need to complete this exercise, you need to verify that they're identities and composition, and those satisfy the rules. Okay, and now a tricky question. What is the co-product in CAT? Yes. So I have two categories, C and D, and I want to take a co-product. What's that?
The product of the opposite categories?
No. So what was the co-product in set? Let's start with that. Yes, disjoint union. So would that work in categories? Yeah, yeah. So we want to take the co-product, let's see, take the co-product here, and, okay, actually this is it. So, okay, so first we can take the co-product of the objects, and then the morphisms will look different, right, because here there are pairs, and there are definitely not pairs here. So we just say that there are two cases now, we're going to do some pattern matching, so I'm going to do case right. So there are two cases. One where we look at HOM C prime in the co-product, and that should be HOM C prime in the original guy curly C. And similarly for curly C. Make sense? Does everybody know? Okay. So I made a mistake of movable board. Okay, so then HOM of HOM in C plus D is going to be Okay, so we can pattern match, let's just say. I don't know what foundations I'm in right now, types or sets. So let's pretend we're a type, and we can pattern match on one of these guys. So we can pretend that we're in here, and then we have, we're looking at C and C prime. So I'm suppressing like the iota or the in left here. Okay, so we have a hum between a C and a C prime that are coming from curly C. So let's let that just be the original hum in C. Or we have D plus, oops, D comma D prime. This is hum D comma D prime. Okay, so this is the same. And then there are two more cases, of course. So if I do C comma D, so where C is coming from curly C and D is coming from curly D, I'm expressing that to be an inlet and in right here, or an iota C and iota D. So there should be an empty set because we don't know how to connect them. And similarly, if we have something from D and something from C, we also don't want them to be connected. We just take the disjoint unit. We just really put, we drew a picture, it would really just be a picture of C and a picture of D just next to each other. Okay.
Why do we have to specify that is it that we don't make them then they're just
Yeah, I mean, we should really here need to supply what this functor does for every pair X and Y in the category. Yeah, so the pairs are either in the form like in left, or something right or something, or in left and left, and right, and right and left. Yeah.
So this why are we allowed to say, because I guess it looks like it's saying that, oh, these morphisms, we're not sending them anywhere. Then is that allowed to? I feel like my question might be too confused.
So they're not a functor. We don't have to send the morphisms anywhere. We just have to say what the morphisms are. I guess maybe this would be my point to this. But I point to this because it's the same like list of things as it is done in a category. We're just showing it as a category. Okay, so now we've produced these two categories. Still some more stuff to verify that they're actually categories. And then if we really want, you can verify that they're actually the bicycle product. Okay. Maybe if you want, for the advanced category theorists out there, if you want an interesting question, we talked yesterday about what a disjoint union is and how we didn't want to say anything about other kinds of unions. So there are other types of unions in category theory where you have some information, where you supply some extra information about what the intersection is. Called push out. Sometimes people, I know some people have been looking at category theory independently. So in set theory, if you have two sets and some information about how they overlap, then you can take a non-disjoint union. And so you can do that in any category, in particular in the category of categories. But if you have some information about which guys you want to overlap, what is the push out, so the generalization of co-product. So maybe I'll give you a tiny instance. If you have a category C that might be very complicated, and there's one object here that you're particularly interested in, let's call it X, and you have some other category D, and you want to say that they overlap just at X. So their overlap is just the object X and the anymorphism of X or something else. Then what is the union of these two guys? So then we goes beyond the lecture, but I need to define that categorically. So that's an interesting question to think about. Okay, so let's do something more interesting. So maybe the most basic, other than what I've already given, the most basic functor that you might have seen, like maybe before this lecture, you guys have seen functors in Haskell, right? So the most basic functor in Haskell is the maybe monad, or the maybe functor, as we call it. The most basic functor, that's not the identity. So here's an example. So now that we have a terminal object, or we have the concept of terminal object, we can consider, maybe I should write this actually. We can consider a category with coproducts, so it's a plus, and a terminal object. So I call that T last thing, right? So we want to consider a category, let me give it a name, C, with coproducts, maybe these look kind of similar. With coproducts that we write as plus, and a terminal object that we're going to write as T. My hypothesis. Then we have a functor. Let's call it maybe from C to C. Okay. And what should it do? Yeah.
It should take the, actually, I have an idea.
Yeah, so we first need to, okay, so you guys all know about maybe in Haskell, right? People? Okay, maybe half of you. Okay, so the maybe monad in Haskell is a functor. You might already know that, you know about Haskell. So in our formalism, we have to first say what those are the objects of C. So we want to take, China right now. We want to take a guy in C to what?
Just X, like just the object, or press E to go.
So just as a constructor, we want the whole type. So we return a type, or sorry, we take in a type, and we return maybe X. Right? Maybe X is a type constructor. We are producing maybe X, and what we need literally by maybe X is this coproduct of X plus terminal object. Make sense? Any questions? Yeah.
So for example, if I have the integers, or I'm thinking Haskell, I understand I can have an integer turn into an integer, but I'm having trouble understanding how the integers have a sum product or especially an initial, or sorry, terminal object.
Okay, maybe I need to provide more information. So I'm working with an arbitrary category C that has coproducts and terminal objects, but what I'm thinking of is that C is set, or that C is the category of types. So maybe in particular the category of types, so I'm talking about Haskell now. So maybe takes in a type and returns a type. The category of types has a terminal object, unit, and it has a coproduct. So I forget how you denote it in Haskell, but maybe it's a plus. So maybe is a type constructor that takes type, return a type. It takes type X, return a type maybe X. Okay? And maybe X is literally X plus 1. Okay, so if you, yes.
Sorry, so what is the, so it X is type, and then plus, and then combine type with maybe,
Sorry, can you repeat your question?
yeah, so, if X is the type, then like what is like plus T doing? Like,
think about like what's actually happening. Okay, you guys might have to help me because I'm not a master programmer. So I forget exactly how you write everything down. But for the maybe monad, to define maybe, you have two constructors. So you have just, right, like this. You have just that takes in an x and produces something in maybe x. And you have none?
Nothing.
Like N-O-N-E? Like that? Okay. Oops, not from x. Is maybe x. So we have these two constructors for the maybe monad, what's familiar, hopefully. Okay. So, right, so what's happening is that when we write something down in Haskell like this, we're giving an inductive definition. Maybe they're letting you know something right now. Which means that you're building X, I mean, hopefully this also mentions your intuition, or maybe what Anya talked about last week, that we're building maybe X from these two things, right? And there's nothing else in there. There's just these two things, right? Nothing else in there. Nothing else in maybe X. So how we should think about that is that maybe X has a copy of X in it, right? Annotated by the word just. Right? For everything in X, there's something in maybe X annotated by the word just. So there's a copy of X in maybe X. And there's this extra guy, none. So what I did here is I sent X to maybe X, and I took a copy of X, that's the left-hand side, and I took something that usually behaves like a singleton, the terminal object. Okay, so we saw that inside, in set, in cat, the terminal object always just has one element in it. Okay, so I took my object X, and I produced a new object that is X plus an extra guy, and that looks like the specification here. Right, so we have X plus an extra guy. Yes. Nothing. Okay. Yes.
Why does it have to be within the same category? Instead of like a category, less from a category that it extended with co-products and.
You could do that definitely, but I guess I'm trying to model the phenomenon that's happening in Haskell, where you take in a type and you return a type. So you take in one kind of thing and you return the same kind of type. Okay. Any other questions? Yes. Yeah. Let's talk about that later. Yeah. So monad is a functor plus x is not. Just like in Haskell. Yeah. So we won't talk about it so much. Yes.
So I guess following with the previous question, if I wanted to have like maybe 0, so 0 doesn't have plus, it doesn't have, I guess the T element.
So what do you mean by 0? You mean the
The
empty
categories, the empty category.
So here I'm working with an arbitrary category C. But let's think about the particular example that C is typed, and maybe like types from Haskell. Okay, pretty well defined. That's a good idea. So I'm going to take in a type from Haskell, X. Maybe that could be the empty type. And then I return the empty type plus the unit type, which is basically the unit type.
But I guess wouldn't that not satisfy the type of maybe here where the C would be 0, but we need to map it to 0 plus 1.
So let's just think about types. As a favorite example of this. But we only need it to be a category with plus as a terminal object for this to make sense. So we take in a type, like 0, and we return a type, like the singleton, like the unit type. Any other questions? Yeah. We can always construct an instance of the return type,
Oh, sure.
because we have this nothing constructor. Yeah, make sense? Okay. So, we have maybe, and we said what it did to objects. Hopefully somewhat clear now. And now we need to say what it does to morphisms. And if we program in Haskell, we know that if we want to show that maybe is an instance of the functor class, then you need to, well, you need to say what it does to morphisms. Right. So, and maybe of x, y, it has to be something from hom type, I'm gonna write it here. Maybe x, maybe y. I don't know why we're going to n first. Okay. So here we have maybe type x, y. Okay, so what should it do? So it has to be a function like this, and what should this function do? Yeah.
If the maybe is the unit type, then just take it to the unit type. But if it has something, then follow the morphism from the original place.
Yeah. Exactly. Okay. Okay, now maybe write something in pseudo Haskell, probably a combination of Haskell and Rock. Okay, so I want to do pattern matching on what is going on here. So I have, this may be a little bit more complicated than I wanted to, but okay. Again, we think just about type and not about an arbitrary category C. So we have a function, like this. So we have maybe x and y. It's going to take in here an f from x to y. Maybe I should write that down. And then it has to produce a morphism from maybe x to maybe y. So just like in Haskell, we can plug in something from maybe x, and then we can do the pattern matching. So maybe f from x to y, and then something from maybe x, which could be something like